So now let's finish up our discussion of power flows and look how we can extend this single section example of a power flow to a multi-section type of an example. And this is an example I'm going to use to kind of discuss this. This case, this is a three-phase circuit, but I'm going to run a balanced power flow in this case. I'm just going to do what we call a per phase analysis just to show the steps. You're not going to be responsible for doing this true three-phase unbalanced. It's just simply going to be too complicated. You're just going to use the computer program MilSoft for that. But I just want you guys to kind of understand the steps that the MilSoft's WindMil is taking in order to get the numbers. So here's 12.47 kV substations. That'd be 7,200 volts line to ground. This is the per phase impedance. We'll just assume we've got the same impedances for all three line sections, and we're going to have three buses, 1, 2, and 3. And each bus is going to have the same amount of load associated with it. And so in this case, if we have this 0.612 plus J 1.26 ohms, in polar, this would be 1.4 at angle 64 degrees. When I talk about these impedances, the subscript corresponds to the from and the to bus numbers. And so like Z01 would be the impedance between bus 0 and 1 in this case. So how would I do a power flow in this particular situation if I had multiple segments? Well, I basically take what I did for the single segment, I just kind of apply it starting at the loads and working my way back up toward the source. And so if I have a source voltage of 12,470 volts, line to neutral, that's going to be 7,200 volts. I'm going to go ahead and assume that the source is going to be at 0 degrees. And when I do my power flow, I'm going to start with a first guess for my voltages, which is going to be at iteration 0, where these are all going to be set to the source voltage as a flat start. So I just basically take what I have for the source, and I just apply it to all the different load nodes as a starting point. And so again, this is the bus number at the bottom, and the iteration number is in the upper right part of the variable. So the first thing I do is I start off by calculating all my different load currents at all the different buses in the circuit. And this is all based on the guess for the voltage. This is at iteration 1 in this case. And what I'm going to do is I'm going to take the power. Now, since this is per phase, I take the three-phase power and divide through by a factor of 3 to get that single phase. And then this voltage is already a line to ground value, so I don't have to mess around with the square root of 3. And for all the three loads, this gives me 46.3 amps. So if I go back to this original circuit, all these different points on all the loads, then what I get is a 46.3 amps. Okay. 46, 46, and 46. Now, what I'm going to do is I'm going to take all these load currents and I'm going to calculate the various line currents. And this is where topology is important, because let's suppose that I want all the different line currents associated with this particular circuit. How would I do that? Well, what I would do is I would start at the bottom of this distribution circuit and I'd work my way up toward the source. So in this particular case, let me just go ahead and erase some of this stuff on here just to make it a little clearer. As far as the sequence of all this, and the sequence is important, I start from the end nodes. If I had 46 amps here and I had 46 amps here, then basically on this line, I would just sum up all the loads and I would get 46 here on the line. You know, I'd get 46 in the line up here, right? Now, if I go up to this particular line section, then what do I have for the net current? Well, not only do I have the 46 amps associated with the local load, but I've got the load associated with all the line segments below that node. All right, so in that case, it's going to be 46 plus 46 plus 46, which is equal to the 138.9 amps. All right, so what I'm doing is I'm taking advantage of topology. If I had a more complex topology, this is actually in computer science what we refer to as a tree structure. It's kind of on its side. But what we would do, we would start from what we call the leaf nodes. These are all the nodes at the end. If we have these load currents, then we work up. We would get the next set of line currents. Then we would keep adding the currents up as we're working toward the top of the circuit or the root of the tree. And basically, this is what I would refer to as the upward sweep. Okay. Now, there's all sorts of algorithms in computer science for doing what are called these tree traversals. And so if you get a book on data structures and you look at the material on generalized tree structures, there's all these algorithms that actually confine the leaves of the tree and actually allow you to move toward the root node in order to sum up all these different line currents. Once you've gone in the upward direction, you did what we call the upward sweep. Then what you would do is you would do a downward sweep to calculate all the different node voltages. And so what you do is you start from the very top of the tree, and then you would calculate the voltage associated with the first node, right? And so V source minus Z01 times I01, this is a line current, is going to give me 7,036. And then what you would do is then you would go to the next level down and you would update those voltages. So as part of the downward sweep, once I have V1, then I can calculate V2. Once I have V1, I can calculate V3. And then I use the currents I just calculated, the line currents I just calculated, in order to update the voltages at 2 and 3. So V2 is V1 minus Z12 times I12. V3 is V1 minus Z13 times I13. And since this is symmetric, it gives me the same voltages in both cases, 6,982 volts. And this is what I would get for the voltages in my first iteration. So I start with a flat start. I sweep upwards, get all the line currents. I sweep downwards and update all the different voltages. And so it's a fairly straightforward algorithm. And the reason I can just simply have an upward or downward sweep is I have no loops. If I have loops like I do in a transmission circuit, then this isn't going to work at all. I got to use something like a Gauss-Seidel or Newton-Raphson. So distribution is a special case as far as doing power flows if we have a radial circuit. So once I've got these voltages updated, then what I would do is I would then update the load currents. Once I have the load currents, I would go ahead and I would update the line currents through the upward sweep. And then once I had those line currents updated, then I would go through and I would get the next group of voltages calculated using the downward sweep. And what you're going to see is you're going to see these voltages are going to start to converge. So if I would compare what I had in iteration 2 to iteration 1, then what I'm going to see is that difference is going to be 0.08 for bus 1, 0.13% for buses 2 and 3. Depending on what my voltage criteria was, I may decide to keep going on, right? But let's suppose this is close enough. I'm going to get close. This time I'm going to get below 0.2%. Then I might just go ahead and stop. And after I've stopped, then what I would do is I would go through and I would do other sort of calculations like line losses. Now in this case, since this is representing 3-phase, even though I'm using a per phase balance model, What I need to do is I need to have a factor of 3 to get the losses in this case. And so then I just do a 3 squared times r in this case. And then this gives me the line losses for all the different lines. And what's interesting is that the losses on this first segment are by far the highest because that first segment is carrying all the current for all the load in the circuit. And this is what we see in real life on distribution circuits, is that the load at the top of the feeder is the highest, and that's where we're going to have the highest losses. So if I did like a color chart and it was more red, more losses, it'd be really red at the top of the circuit, and then not so much I squared R loss in the toward the leaf nodes of the circuit. So we could put this stuff in all these values into a table, and then you would show, what are the voltage magnitudes and the line currents and the line losses. And this is a program like MilSoft does. The only real difference is instead of these calculations being all in terms of regular complex numbers, these calculations would all be in terms of matrices or vectors, right? So I'd be calculating a 3x1 here if it's 3-phase, or a 2x1 if it's 2-phase. And then these would be 3x3 or 2x2, or maybe 1x1 matrices. Basically, that's kind of the what's going on under the hood. And WindMil is doing these same types of calculations, but they're all in terms of matrices, right? And again, if you couldn't really do this by hand anymore, you would really have to write a computer program in order to do these sort of calculations. And that's kind of what WindMil is all about. So anyway, I could build this circuit actually. I mean, I could build a circuit and I can do these similar sort of calculations, and this shows the same 3-node circuit. Now, what I'm going to show you is what this would kind of look like if I would plug this into a 3-phase framework, because that's what WindMil does. So if this is a 3-phase framework, then what I would do is I would put a line model in here, which I would have like the actual conductors plugged in. I would have some information in here in the spacing, and then what I would get is I would get this 3x3 matrix for the line. In this case, you could see that this is imbalanced, that these off-diagonal terms are all different, right? And so I could go through and I can start making use of the load allocation now. In this case, I'm just assuming that I've got basically a 3000 kVA transformer at these different node points. Got 1000 kVA per phase, so that would total up to 3000. So you can think about the 3000 kVA transformer each of these 3 buses. And what I'm going to do is I'm going to use load allocation to allocate that load that I had before. And so I had originally in this circuit, if we go back to the beginning of this example, we basically had a 1, 2, 3, we had a total of 3000 kVA at a power factor of 0.85. And so that would have to sum up to the top of the substation. If we had a measurement there, then what we would measure, take the 3000 times 0.85 power factor, that's 2550 kilowatts. If I plug in here for the 85%, MilSoft or WindMil will auto-calculate the K-bar. And then what I would do is I would set up a load control point at the top of the circuit. And I'll go through this in the next lecture when I go into the details of doing WindMil analysis. But what you do is you set up what's called a control point at the top of the circuit. This is where you have the measurement. And I would plug in this as the measurement value. And then what I would do is I would select an allocation method. And what this is telling MilSoft, the WindMil program, is that I want to use transformer KVA as the method of allocating load. So I'm going to ratio out depending on the KVA size I have plugged into the billing load. So when I run this, then what this is going to do is it's going to put the calculated load values into all the different load points. You could see that I've got this 3000 kVA transformer size at each load, and then you can see how this actually allocates it down by phase. And since all the nodes are the same, it allocates the same amount of P and Q at each of the load, and it breaks this down into phase A, B, and C values. Now, one thing that's going to give us a little bit of difference in this case is that there are some losses in here in this circuit. So at the top of the feeder, I'd actually have a little bit more. I'd actually have a little bit more than that 2,550, but we're just going to neglect this loss effect for now because it's pretty small. And then what you could do then is you could take a look to see, you know, what it does for the calculated load. And you can see what it's going to do. It's going to auto enter all these values based on the load allocation procedure. Then when you look at the unbalanced voltages in the circuit, if you have non-transposed lines, what you're going to see is that you're going to see these voltages are going to be slightly different per phase. Not a huge difference in this case, but you see the voltages are going to be slightly different. And then if you want to go ahead and transpose, you can go ahead and transpose, or you could run the balance type of analysis. And what you're going to see in this case is you're going to see these voltages, and where I had gotten 6,973 doing my little analysis before, kind of piecemeal by myself, you can see what WindMil calculates is it calculates 6,981, which is pretty close considering that there's a slight difference between the two studies in terms of the loss values. So anyway, when we do this for the project, you know, we're going to do the unbalanced analysis. The only reason I'm doing the balanced analysis right now is so I can do the comparison of doing things by hand. But in reality, we're typically going to run this. We're going to run this unbalanced. But anyway, just kind of show you how this kind of compares. And again, the 6,981 we get using the balanced analysis, it's not the highest value, it's not the lowest value, it's somewhere in between, you know, what we would actually get if we did the more detailed analysis. You can kind of generalize this algorithm if you want to write this algorithm on your own. This shows you on these few slides, you know, what this would actually look like. Again, you have to have a radial structure. You cannot have loops in the circuit for this to work, which is the case with distribution. So in a generalized manner, what you would do is you start off by initializing all the bus voltages. Normally, this is a flat start where you can use nominal. Now, if you're running power flow over and over and over again, making a small change between each study, you could actually take the voltages from the previous load flow. You can do this, you can do that as well, and that'll actually give you faster results. But you just make some initial choice. You would have an iteration counter. So you start with k equals 0, and then you would increment the iteration counter. You would update all your different load voltages at all the different nodes in the circuit. And then once you've done that, you would sweep up toward the source and you would calculate all your different line flows. All right. And so this is 3 by 1 for each bus. Again, you're doing this for phases A, B, and C. Then what you would do is you would sweep down starting from the source, and you update all the different voltages in your circuit. So you do this section by section, starting at the top of the feeder and going toward the leaf nodes. And again, this is a tree traversal type of approach. It's a tree traversal algorithm, as I mentioned before in computer science. They have all these different codes you can get, which does this tree traversal, sweeping in both directions. Then once you have the voltages updated, what you can do is you can do a check on your tolerance. You compare the last set of voltages to the previous set of voltages. You see they're all within a given set tolerance, and if they're within a tolerance, you're done. If they're not, you start back at the start back and you update your loads again, load currents again, then get a new set of line currents and get a new set of bus voltages, and you just kind of keep iterating over and over and over until you're done. So anyway, that's kind of the generalized sweep procedure if you want to write a computer algorithm around this. Kirsting's book that I use for reference also has this material in there, but he uses a slightly different approach. I'm still giving this to you as a reference. He uses a very, very similar approach. He would call that a ladder technique. But what he does in there is he uses what's called an acceleration factor to make it converge just a little bit faster. And so besides just changing the voltage, he does a little bit of a boost to that change. It was called an acceleration factor to make it converge faster. But otherwise, it's basically the same sort of thing he explains in his book. So Kirsting goes through a lot more detail about how do you model transformers, and if you have transformers in the circuit, then how do you include those in this sweep technique and stuff like that. If you're interested in this would be a good book to read if you wanted to like write a more serious power flow code on your own. And a lot of this was adapted by the engineers at Millsoft for the WindMil program, because they reference this book a lot. And so if you wanted to know more about what happens under the hood in the WindMil program, you know, a lot of that stuff is discussed in Kirsting's book. And if we had more time in this class, we'd get into this more in detail and how do you do like 3-wire delta connected circuits and things like that. But that's a little bit more that I want to get into in this particular class, but it is talked about more in Kirsting's book. So this is pretty decent reference if you want to learn a little bit more how to write a distribution power flow program. Okay, so now that we've kind of looked at power flow, what I'll do in the next lecture is I'll go back to Millsoft and I'll do a kind of an extended example and show how you actually build a circuit up from scratch, and then how do you do the load allocation and everything else, and get into a lot more detail about how you could do this stuff from zero, as opposed to taking these examples that I posted up on the Millsoft, on the Moodle site. All right.